All right. Good morning, everybody. Thank you for joining our webinar today on April 9th, 2025. The topic is behavior of self-tapping screws in glulam under moisture content change. We have a guest speaker here today, Sarah Kipor, who will be sharing this presentation. If you are watching from a computer, at the top bar, you should see an option that says Q&A. If you have any questions throughout the seminar or the webinar, please post them in there and we will answer them at the end. If you're on your phone, you should see three little dots on the bottom right-hand corner. And when you open up that, you will also see the option to enter the Q&A section as well to drop your questions throughout the presentation. So without further ado, Sarah, all yours.
Thanks, Chris. Hello, everyone, and thank you for joining this meeting. My name is Sarah Kapoor, and I'm a master's student at the University of Alberta. Today, I'm going to talk about the behavior of self-tapping screws in glulam under moisture content change. It was a part of a collaborative project between University of Alberta and Rothoblaas. And the target of this presentation is to enhance understanding about the behavior of the self-tapping screws under moisture content change in timber connections. So I divided this presentation into different parts. First, I will go through the problem statement and motivation, the research objective of this project, and then I go through the effect of the torque on self-tapping screws, the effect of the moisture content change on this type of connection, and finally, I wrap it up with the conclusion. Mass timber projects across North America are often large in scale, which leads to prolonged exposure to the elements during construction. Frequent rainfall and variable climate conditions further increase the risk of the moisture-related damage, and the effective moisture mitigation goes beyond simply covering the wood. It's closely tied to the design and performance of the connectors. Well-designed connectors can significantly improve the structural resistance to moisture ingress and make them an essential part for any mitigation strategy. However, implementing successful strategy is not possible without a clear understanding about how moisture affects on this type of connection. This knowledge is essential for developing targeted solution and guiding informed decision related to scheduling, detailing, and designing of the structures. Self-tapping screws is one of the common form of fasteners in timber structure, especially in hybrid structures when we have the steel, wood, and concrete. But sometimes some parameters and some factors affect on the performance of self-tapping screws, such as design, material, installation, and environmental condition. Sometimes these factors or combination of these factors result in failure of self-tapping screws and make some challenges for the structures. For example, we heard about the hydrogen embrittlement. We know that in hardened screws, when they are under the tension, presence of the moisture increase the risk of the failure. I mean the hydrogen embrittlement failure. I'm not going through this because I know that there are another webinars which go through the hydrogen embrittlement in details because Rothoblaas is working on this project in detail and they will provide another webinar about that. Also, based on the research and test which was done in Rothoblaas, they found that the inclined screws are more susceptible to failure in presence of the moisture. The target of this project was focusing on effect of the installation torque and moisture content change in a steel-to-wood connection when self-tapping screw is installed perpendicular to glulam without any inclination inside the glulam. What motivated us to continue this project was that the failure of self-tapping screws due to increasing in surrounding moisture content was reported by some contractor in North America. This project was started in 2020. It was a collaborative project between University of Alberta and FB Innovation. They did lots of tests on CLTs, glulam, and different self-tapping screws from different manufacturers. Under the moisture content change, they couldn't find any failure. So we still heard about this problem, and we decided to continue this project. And I joined this project from 2022, and after that, we collaborated with Rothoblaas. We believe that in this type of connection, I mean that steel to wood connection, when wood absorbs water, it swells. This swelling adds additional stress to self-tapping screws because the steel plate at the top acts as a restraint. So when wood absorbs water, it cannot move freely. So it adds additional stress to self-tapping screws. When it combines with the stress caused by torque, it increases the total stress in self-tapping screws, and it may result in failure of self-tapping screws. So if we could find the stress distribution on self-tapping screws by using some failure theories, such as one Mises theory, we can find the critical point, and also we can find the stress on self-tapping screws, and we can help designer to have more and better understanding about what's happened in this type of connections. So the objective of this project was evaluating the behavior of self-tapping screws under the torque and moisture content change, and also develop a model for self-tapping screws in a steel-to-wood connection under moisture content change. In order to do that, we divided this project into different steps, 2 steps. In the first step, we focus on effect of the torque on self-tapping screws, because sometimes the effect of the torque in the design phase or in the test were overlooked. So we did the experiment, and also we use the analytical model in this step. In the second step, we focus on effect of the torque and moisture content change on self-tapping screw. In this phase, we conducted several tests. We used the analytical model to find the stress on self-tapping screws. And finally, we developed a numerical model to find the stress distribution under non-uniform moisture content change, which happens inside the wood. We start with a preliminary test, because we need some parameters as an input for our analytical and numerical model. So we start with a tension test because we need some tensile properties for self-tapping screws, and also we want to know the moisture content inside the glulams in our timber member. And also in this stage, we try to find the analytical model and simulate the moisture distribution inside our samples. So we start with the tension test. We use the universal tensile test machine. And as you can see in this picture, we've in this research, we focused on partially threaded self-tapping screws, HBSP, with 8 millimeter diameter and 160 millimeter length. So we made special grips and fixture to make sure that our experiment is based on the standards. And also we use a 50 millimeter gauge length for the extensometer. We found the load displacement, and based on that, we found the stress strain curve for this self-tapping screws because we need some inputs such as Young modulus, yield strength, and ultimate tensile strength for our simulation. The second part focused on finding the moisture content change inside our samples. We did several tests to find the best method for finding the moisture inside the wood. Finally, we used the insulated electrode pin to find the moisture inside the glulam in different layers. And also in this step, we developed a numerical model as well. In order to simulate the moisture transport inside the wood, we need to have the diffusion coefficient. So we did the parametric study, and based on that, we found the best diffusion coefficients for our samples. In this simulation, we used the single thicken method, which is a practical method for finding the moisture transport inside the wood, which is based on the Fick's law. And based on the Fick's law, the moisture transport or move from the high concentration to low concentration area. In order to simulate this movement and this moisture content, non-uniform moisture content change, we use the hydrothermal analogy method in Abacus software. And here you can see the results. This result is a sample of how moisture distributed inside the glulam when only 2 layers of glulam are exposed to the water. After a few hours, you can see these areas, which are red. They reach to around 30% of the moisture content, which is the fiber saturation points. And after 48 hours, you can see how moisture can be distributed inside the wood and our samples when only 2 layers of glulam are exposed to water. So we start with our main test. And our target in step 1 or drying condition was finding the effect of the torque on self-tapping screws, because as I mentioned, usually the effect of the torque over-torquing was overlooked. And also we know that when we apply the high torque and over torque the screw, we can damage the screws and sometimes we can fail the screws. So in order to find the stress on self-tapping screws, we started with dry condition and step 1. The objective of this step was measuring the failure torque and investigating the correlation between the clamp force and torque. Also, we tried to focus on the analytical model as well, because we know that there are some equations and formulas available for bolts and nuts, and also it was used for lag screws in wood, but we were not sure that whether we can use that for self-tapping screws or not. So we did some tests in order to make sure that they are applicable for self-tapping screws as well. And the objective of this part was evaluating the relation between the torque and clamp force and finding the installation torque based on the bearing torque and threaded torque. And finally, based on these, we can find the stress on self-tapping screws. So when we apply torque on fasteners, like self-tapping screws, in fact, we are increasing tension inside our fasteners, which called preload, and we are increasing the compression between the members, which called the clamp flow. In case there is no separation and there is no external load, this preload is equal to clamp flow or clamp force. In order to measure that, we place the load cells between the steel plate and our glulam to measure this load. So in this part, I mean in drying condition in step 1, first we made a pilot hole and then we installed the self-tapping screws. When the head of a screw reached to the steel plate, we used the manual torque wrench to tighten the screws. We divided our samples into 3 different groups. In group A, we increased the torque incrementally. In group B, we increased the torque continuously. And in group C, we increased the torque to different level. In group A and B, we increase the torque until we get a failure. But in group C, we just increase the torque before getting any failure. So in group C, we don't have any failure. In the first part, we focus on finding the correlation or relation between torque and clamp force. As you can see in this table, in group A, we applied the torque until we get the failure. We increased the torque 2 Newton meter by 2 Newton meter. And then by using the load cells, we measured the clamp force and we found the torque coefficient. In this case, the torque coefficient was around 0.4. So in group B, we increase the torque continuously until we get the failure. And you can see how much torque we could apply. And then same as the previous group, we measure the load or clamp force, and based on that, we found the torque coefficient. You can see in the case we applied the torque continuously, the maximum installation torque was 40. But in the case we increase the torque incrementally, the maximum installation torque was around 51, which is higher than this case. Also, you can see how installation and also the speed of applying the torque affect on this torque coefficient. We did the same thing for group C. I mean that we increase the torque continuously. In 3 sample, we increased the torque until 18 Newton meter. In 3 sample, we increased the torque until 30. And in 3 sample, we increased the torque about 37, a little bit less than 37 because we don't want to have a failure in this group. And we found the torque coefficient. You can see that in these two groups, because we applied the torque in the same condition and with the same speed, the torque coefficient is kind of similar. It's around 0.33. So in the second step, we focus on, in the second part of step 1, we focused on the installation torque. Because we know that the installation torque is a combination of a bearing torque and the threaded torque. So bearing torque is because of the friction between under the head of the screws and the steel plate, and threaded torque is because of the friction between the threaded part and the glulam, and also the shape and the profile of screws will affect on threaded torque as well. So we try to find the bearing torque and threaded torque by using these equations, and you can see the results here. We found the bearing torque and threaded torque by using the force which we found from the load cells, and by which we found the installation torque. We compare our result with the experimental one, and you can see there is a good agreement. In the relative difference was the maximum relative difference in one case was around 16%. The reason we did that because we want to find the stress on self-tapping screws, and we need to know about the threaded torque. So in this part, we focus on finding the stress on self-tapping screws. So as I mentioned, we did a tension test, and you can see the results here. These screws are failed under pure tension, and these screws are failed under pure torsion. And you can see that the failure in these tools are different. So this is why we thought that this is something important when we are over-torquing our self-tapping screws, and it's the effect of the shear stress. So in the case we over-torque the screws, we have axial stress and shear stress. Therefore, we use the von Mises stress to find the stress on self-tapping screws. And you can see how shear stress affect on the results. In the failed screws, in the in group B, we calculated the von Mises stress, and we found that the von Mises stress is in these two cases was more than the yield strain, and that's why we get the failure in these screws. The second step of this project focused on the effect of the torque and moisture content change on self-tapping screws. In order to increase the moisture inside the glulam, we attach a bucket of water to our samples. So In order to increase the level of the moisture, we increase the height of the bucket, and you can see it in next slides. The target of an objective of this part was measuring the load caused by torque and moisture content change on self-tapping screws. Same as the previous steps, we used the analytical model and we calculated the stress on self-tapping screws. And finally, in this stage, we developed a numerical model to simulate the moisture and also a stress on self-tapping screws. Same as the previous steps, in order to measure the load caused by torque and moisture content change, we place the load cells between the steel plate and our glulam, and we increase the moisture inside our samples. So we divided this step into different rounds. In the first round, our target or our objective was finding the relaxation phase and investigating the relaxation phase. And also we want to measure the axial force in wetting condition. We divided our samples into two different groups. In group A, 3 samples were self-tapping screws were installed with recommended torque, and in group B, which was 3 samples, they were installed with over torquing around 30 Newton meter. And also we poured the water inside this bucket to increase the moisture inside our samples. And the level of water in this case was 48 millimeter, which was less than 2 lamellas. Here you can see the results of load, which was measured by the clamp force. In group A, which we increased the torque until 18 Newton meter, you can see how the load increased during the tightening, and only few seconds after installation, you can see this load start decreasing. This phase called relaxation, and it happens for all connections and all fasteners. So, but it depends on the material, and there wasn't any data, many data about how this relaxation phase would be in timber connections. So we stayed for about 24 hours to see how this relaxation phase would be. And after that, we poured the water inside the bucket in order to see the effect of the moisture content change on axial load, which was measured by the load cells. So you can see in this phase, in the relaxation phase, around 24% of clamp force decrease. We did the same thing for group B. We increased the torque to 13 Newton meter, and we stayed for 24 hours. And after that, we increased the moisture content. So in this phase, for group B, the relaxation was about 28%, which means that 28% of this clamp force decreased over relaxation phase. Here you can see the summary of the results and the effect of the relaxation after 24 hours, and also the final load, which was measured by the load cells. And this figure shows the importance of the installation torque, because in sample 4, 5, 6, we applied the torque about 13 Newton meter. The level of the moisture was the same, but in sample 4, 5, and 6, the over torque was higher than these samples. And you can see the final load in this group B was higher. Round 2 of the test focus on the combination effect of the over torque and moisture content change on axial force in self-tapping screws. In this round of the test, we increase the torque until 37 Newton meter. And also our target was finding the effect of the moisture, different level of the moisture. So we divided our samples into 3 groups. In group A, only 2 layers of glulam were exposed to water. In group B, 3 layers were exposed to water. And in group C, we wholly submerged our glulam into the water. In this round, as you can see here, same as the previous round, we applied the torque, and we over torque the screws until 37 Newton meter. In this stage, we didn't stay for the relaxation phase, and we poured the water only few minutes after the installation, and you can see the results. The results shows that this axial force, which is caused by the torque and moisture content change, starts to increasing first until it reached to the peak. And after that, it's decreased slightly. For group B, we exposed 2 layers to water, and we did the same thing, but in this stage, we stayed for about 5 hours to see the effect of the relaxation for 5 hours. And then we poured the water inside the bucket to increase the moisture, and you can see the results. Same as the previous one, this load increased until it reached to the peak, and after that, it decreased. And here you can see that in this figure, that since we exposed more layers to the water, this decrease is more significant. And in round 2, group C, we increased the torque around 37 Newton meters, same as group A and B. But in this case, we submerged the whole glulam inside the water, and you can see the results. So we measure the one Mises stress by considering this fact that for the sample 11, which is the worst case scenario, so we measure that by considering this that the moisture only affect on the axial stress, and the shear stress only is due to the insulation. And also based on the previous round, we found that there is a relaxation. So we measured the one Mises, and we found that in this case, I mean the worst case, which is sample 11, the one Mises stress is below than 1000 megapascal. It should mention this point that we opened all the samples, and we couldn't find any failures in self-tapping screws, even under the severe moisture content change. In order to compare the results in round 2, we get the average of group A, B, and C. And you can see how this load and this axial load is different in group A, B, and C. But in all groups, they follow the similar trend. First, the load starts increasing until it reaches to the peak, and after that, it's decreased. This is because when wood absorbs water, it expands, and this expansion starts from the edges and outer part of the glulam. So when it's expand, it tries to push the steel plate to the top, and it increases the axial load on self-tapping screws. But after a while, this moisture penetrates inside the wood. So we know that below the fiber saturation point, material properties of wood change significantly with the moisture. So its effect on the stiffness of whole structures. And also based on the literature review, moisture content have negatively affected the withdrawal properties of connection. So the strength and stiffness of the connection decrease as well. That's why we see this load starts decreasing only few days after moisture penetrates inside the wood. Finally, in round 3 of this test, we want to verify that hydrogen embrittlement failure does not occur with correct installation. In this round of the test, we divided our samples again to two different groups. In group A, we fully submerge our sample into the water. And in group B, we put our samples upside down into the water. Our target was finding whether we could find any failure under the severe moisture content or not. And also in this step, we didn't use the load cells because we want to increase the penetration length. So here you can see in this picture, you can see that there was no failure in self-tapping screws, even under the severe moisture content change. Finally, we tried to develop a numerical model, and maybe you ask me why we need the numerical model, because sometimes doing tests are time consuming and also they are costly. They need lots of investment. And also sometimes it limits number of the specimen or material we can test. Sometimes it's not possible to do the test. For example, in our case, we cannot measure the moisture with the electrode pin in all layers of glulam. So if we could use the numerical model, we can have better understanding about what happens inside the wood. That's why the role of the computer and simulation is important. So we use the finite element analysis software, Abacus, in order to find the stress distribution under uniform and non-uniform moisture content change. And here in this presentation, I only focus on the non-uniform moisture content change because the time is limited. And also, I should mention this point that we use the 2D axisymmetric model because of the computational cost of the 3D is so high, because we consider the thread and effect of the thread on stress concentration. So we model our glulam, and each layer, in each layer, we consider the effect of the growth ring, because we know that the wood has the orthotropic material and the material properties change in radial, tangential, and longitudinal direction. We simulate the growth ring for each layer of glulam. And we also consider the effect of the moisture on material properties of wood. We opened most of our samples, and in our samples, we couldn't find any severe damage or severe crack or withdrawal. That's why in our simulation, we didn't consider the effect of the withdrawal failure or any kind of crack. And we, as I mentioned, we use the two steps Abacus, two steps numerical model by using the Abacus software. And we consider the effect of the torque and the effect of the moisture content change in the short-term condition, because we only put our samples exposed to water for only 1 week. So we didn't consider the effect of the creep and mechanosorptive strain. And here you can see the results. The green dashed line shows the result from the numerical analysis. This is the stress caused, the axial stress in self-tapping screws caused by torque and moisture content change. Finally, I should say that based on this research, we found that the analytical model can give us a good estimation and can predict the relation between the torque and the clamp force. Also, by using the analytical model, we can find the installation torque and the threaded torque. And by finding these parameters, we can find the we can find the stress on self-tapping screws by using the von Mises theory. Also, as I mentioned, the relaxation phase has effect on the clamp force. around 25 to 30% of clamp force decrease after 24 hours after installation. Also, we found that the combination of the torque and moisture content change can increase the axial stress in self-tapping screws up to 60% of ultimate tensile strength of self-tapping screws. So, based on what we found, due to moisture content change and non-uniform moisture content change, which happens inside of the wood, the axial force increased on the first day, and it reached to its peak. But afterward, it started to decreasing, and there was a greater decline as more layer exposed to water. In worst scenario case, we measured the stress on self-tapping screws, and it was less than the yield strength of self-tapping screws. And finally, we could develop a model by which we could find the stress on axial stress in self-tapping screws. For the future work regarding the analytical model, it is recommended to extend the current analytical model to predict von Mises stress due to the external torque and moisture-induced swelling and the potential stress relaxation, because there wasn't many data about the stress relaxation, and we consider some assumption. More research is needed in these areas, and also regarding the material properties. Future experimental work should be focused on measuring the friction coefficient as well as assessing the effect of the moisture on relaxation in tensile force within screws, and also the effect of the moisture on properties of the wood. Regarding the hydrogen embrittlement in hardened screw, it is suggested to evaluate a potential influence of the embrittlement on a screw's strength and compare these findings with von Mises stress resulted from the analytical model. Thank you for your attention, and I would be happy to answer if you have any question. Thank you for your time.
All right, thank you, Sarah, for your informative and very interesting. I have one question for you,
Sure.
since there is no question here in the comments. So my question is about modeling modeling wood. So you mentioned that it's orthotropic material. I just want to know the material model. Was it like in terms of, is it linear elastic?
Yes, it was linear elastic. Yeah, we didn't consider the effect of the plastic because we didn't find any severe damage or any kind of failure. We only, in the simulation, we consider the effect of the deformation in wood, which is under the linear elastic region.
Yeah, I think which I think it makes sense, because if you consider linear elastic, you're dealing with higher stresses. So yeah.
And our target was finding the worst scenario case, because we heard that there was a failure on self-tapping screws only because of the moisture content change. So we tried to focus on the worst scenario case and and we go with the simulation in which we get the higher stress on self-tapping screws. Because we found that, for example, if we consider the withdrawal failure or any kind of failure, because in previous research, they consider that maybe there is some failure, and they used some parameters such as the cohesive or something like that. So in that case, we calculated that, and we found that in that case, the stress on self-tapping screws is lower. But our target was finding the worst case scenario, and that's why we only considered the deformation, and we didn't consider any kind of crack or separation.
Yeah. And I have one more question for you.
Mm-hmm.
It was a really interesting webinar. So for the test you've done, I just want to confirm that you've never done for the test, never gone above 1,000 megapascal for the load. Yeah.
Which one?
For the test you've done, like you mentioned the 1 meters stresses were like around 1,000 megapascal. That you like calculated. I just want to know in the test that you've done. So none of them have been like gone beyond 1,000 megapascal. The stresses on the screws. I mean.
Yeah. So what we calculate the 1 meter stress by considering some assumption. What we measured in the test was the load caused by moisture content change, and also we considered the effect of the torque as well. But in the test, we couldn't find any failure. We did lots of tests on different, with different condition, with different torquing level, and we couldn't find any failure. Based on that, we calculated the 1 meter stress, and for the wet condition, we calculated the 1 meter stress by considering some assumption. The first assumption was considering that the moisture content only affect on the axial stress, and shear stress is caused by the applied torque. And we know that based on the formulas and equations which I showed, we know that the shear stress is related to the threaded torque. And this threaded torque is related to the clamp force, which is decreased over time because of the relaxation. So we consider all this together, and we calculated the 1 meter stress. Based on that, in the worst scenario case, these 1 meters was less than 1,000 megapascal. And less than the yield strength of self-tapping screws. And it shows that we can use the 1 meter stress to find the stress on self-tapping screws.
Yeah, awesome. Yeah, thank you very much.
Perfect, thank you. If there are no more questions, I will say we come to an end here. I just want the people that are still here to inform next week we have another webinar about the hydrogen embrittlement. We spoke a bit in the beginning. There you will get more information. You can also register on that on our website or on the links. For now, I say thank you and a good day.
Thank you all.